Yeah.
It started ringing. Yeah.
See this performance, so I was wondering.
And they don't pay enough. We'll see.
Oh, it's for you. I'm not afraid.
I was yesterday.
Consider this Friday.
Started in March.
Oh, yeah, okay, I'll remember. Right.
Evaluating range practice.
That's better than those little Pez phones.
Salaries.
That's awesome. Sounds like I have very good results.
All right, let's get started. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is one of our own faculty members. It's Dr. Larry Townsend. Larry received his degree in physics from the U.S. Naval Academy in 1969, and then he continued his education at the Naval Postgraduate School, getting a master's degree in physics, and then he served in the Navy for 8 years. 2.5 of those 8 years were spent underwater in the submarine fleet. After getting out of the Navy, he entered the University of Idaho and worked toward a PhD in physics, which he received in 1980. And then subsequently he spent 15 years at NASA's Langley Research Center, becoming an expert in space radiation protection. He joined the University of Tennessee faculty in 1995, and we are indeed glad that he's here. The subject of his presentation today is hazards of solar energetic particle events during human exploration missions in deep space. Larry?
Thank you, Lee. I apologize for the background on this particular slide, but it's got an interesting story. And in fact, it's interesting enough that I decided to show it to you again, but without the lettering so you can look at it. Now, if you look closely, what this is this is the setting sun. The location is the mountains near Boulder, Colorado. This happens to be right behind the Space Environment Center, which NOAA has in Boulder, outside Boulder. This particular figure is of the setting sun, and if you can see him right here, there's a person standing in the rocks. That person is the one who took the picture. Turns out it's the postdoc whose job it is to continuously catalog pictures of the sun and make notations about what he sees and so forth. And in this particular case, the individual realized one day that the sun was setting in a location that he knew exactly where it was because he'd been hiking there before. So he figured out the next time that the sun was going to set in that location, took the afternoon off, hiked up there, and got himself in the picture. The picture became so popular at NOAA that the next time the sun sat in the same place, everybody from the office tried to get in it. What I want to talk about today are solar particle events. We'll start with an introduction, talk briefly about where solar particle events come from, show you what their spectra look like. Then we'll talk, I'll explain to you a little bit about the transport and shielding aspects of them, but what I really want to get to are what happens after the solar particles pass through whatever material they're going to pass through and interact with the crew. So we're going to spend some time talking about solar particle event doses, going to put some of the risks in perspective from those particular doses. I'm going to talk briefly then about forecasting doses. It's a project that we have going on that I got interested in some years ago, partly because somebody told me it couldn't be done. And turns out that we've had some success with it using two different approaches, and I'm going to go through those. One of the approaches was John Neal's dissertation, and the other approach is Jenny Hoff's, and then I'll stop with some concluding remarks. The types of particles that we're interested in for space radiation protection purposes in general consist of these energetic solar particles, mostly protons, some alphas. Nominally about 10% of an event is composed of alpha particles. And then some heavier ions, even coming from solar particle events. Typically we ignore the heavy ions. And the reason is because, as you'll see later on, the spectra from these events are soft enough. In other words, the fluence versus energy curves fall off fast enough that the particles just don't penetrate. And so we tend to focus on the protons and to some extent the alphas, but since the proton dose really dominates, in most cases all I'm going to present are calculations of the proton dose. It also helps for comparison purposes at times between different events, because for some of the older events we don't have alpha spectra. So it's hard to talk about one event versus another if you don't have them on equal footing. High energy galactic ions that are part of the galactic cosmic ray spectrum, we're not going to talk about those today. We'll save that for a different talk. And then the trapped radiations, the latter two are important for the space station, but again, since we're looking at deep space and we're looking at solar particle events, we'll tend to ignore them. The space radiation environment is complex. Basically, you're looking at an environment where you have, in essence, just about anything that's in the periodic table in the environment. And the energies that these particles have range up to, in some cases, as high as 10 to the 20th electron volts. Okay, so we're talking about a very large energy range, and you're talking about a large number of particles. From the cosmic ray perspective, mainly we're interested in particles below iron. Iron being the most abundant heavy nucleus and being one of the most damaging. After that, the cosmic ray spectrum falls off pretty rapidly. In the case of the Van Allen belts, they're important for operations in low Earth orbit. If you get into high latitudes, where the orbit is such that it comes near the poles, then galactic cosmic rays can also become important. And so that's the case, for example, with the International Space Station, which is in a 51.6 degree inclination orbit. About half of the exposure the crews get every day are from galactic heavy ion or galactic cosmic rays, which include the heavy ion component. The other half comes from passages through the South Atlantic anomaly. But again, that'll be another lecture. In the case of solar particle events, they're important for missions outside Earth's magnetosphere for two reasons. One is that they will give you both the possibility of an acute exposure as well as some sort of a chronic exposure. In the case of acute exposure, you're worried about acute radiation syndrome, worried about cooking the astronaut, so to speak. In the case of chronic exposures, what you're worried about is increased probability of cancer mortality. And that'll be the subject of what we're talking about today. In the case of galactic cosmic rays, besides the impact that they have on space station, they're also important for missions outside Earth's magnetosphere. The issue here, though, primarily is one of chronic exposure. The doses from these events from these particles are just not large enough to create any sort of acute effects. Typical dose, for example, during periods of maximum cosmic ray intensity, which would be during periods of solar minimum, is something on the order of 20 centigrade a year for a dose, which is about 20 rads, which is not a large dose. The problem here is that the Q values for these are quite large, so the cancer probability is pretty large. And there's also the possibility of all kinds of unique effects, because you really have a particle that dumps a lot of energy into a very small volume and will pass through multiple cells, causing damage in the case of a single particle. If we focus on solar particle events, this particular picture, which I got off of I think it was off the SOHO website, which is one of the satellites that does solar observations, gives you some feel for the magnitude. What this is this is a piece of plasma, some sort of ejecta from the solar surface that's coming out. So this is probably some sort of what's called an impulsive event. To get the size of it in perspective, this little blue dot right here is the Earth. And so that's the size of the Earth in comparison to the size of these things that come off and in comparison to the size of the sun. So you can see that we're talking about phenomena that cover vast parts of space. One of the major ones we're concerned about is what's called a coronal mass ejection. And here what happens is the sun actually ejects part of the corona. It's got to do with the interplay of the magnetic fields and the fact that the magnetic fields finally loop and break off. And what you'll end up with in this case is you'll end up with a large quantity of material coming off, usually looking something like a bubble. Now, to put this size in perspective, the white circle here is, in fact, the physical size of the sun in this image. The rest of this disk is there to block out the sun and the corona near the surface of the sun, so that you can see the outer reaches of the corona and it's not blocked out by the light. This particular event happened on the 27th of February 2000, and you can see the size of it. It's relatively large. These particular events here, these things here, are what in fact create solar particle events. This is an image of the same one taken with a different filter, and this is a little bit later. This is at about 6 hours beyond the previous one. So here's that same coronal mass ejection, which has now gotten much larger if you compare it to the size of the sun's image. And these things will come off. This particular one is a sort of a time sequence. This one happens to be for an event that occurred in November of '97. This, by the way, the little light thing that sticks off the side here is an artifact in the image. It's actually the holder that holds the disc that blocks the solar image. But this is what this particular event looked like at around noon. 30 minutes later, this was what it looked like. Notice that gotten quite a large ejection, and it comes off pretty quickly. This is approximately 3 hours later. Notice that the picture is getting a little fuzzy. The reason that the picture is getting a little fuzzy is because this particular event also shot particles back along the magnetic field lines that connected with the detector that's taking the images. So what these dots are, these are actual impacts of solar protons on the detector that's taking these images. About half hour later, this is what the event looked like. And it's possible in some of these to get what you call a halo event, where this piece here actually extends all the way around the surface. And it just looks like a ring that gets larger, and then eventually what happens is the image gets white as all the particles arrive at the detector. And that's one that you know has hit you. If it just goes off to the side and you never see all this speckling, then you don't worry about them because it means that they're not connected to where you are. They've gone off somewhere else in space. Some of these events will put out as much as 10 to the 51 ergs. For those of you that can remember what an erg is, it's an energy unit in the CGS system. I never bothered to convert it. Being physicists, we always use ergs. One of these days I'll put it in foot-pounds. All right, solar particle event proton spectra. What we do is we take these spectra and we parameterize them, because what we want to do is we want to put this information into a transport code. Use the transport code to transport the incident spectrum through the spacecraft and through the overlying body tissue, so that we can calculate what the doses are at particular organs that are of interest, so we can look at what the biological effects might be. Now, these particular spectra are modified quite a bit by overlying tissue. Some of us are pretty good shields for our own internal organs. Others are not. But the way we do this is we use what are called integral fluence values, or fluence values. It's basically the integration of the flux over time. We use those values, which we get in the case of the August 72 event, which I'm going to show quite a bit of results from, since it was the largest dose event that we have data for. That data came from a 1972 NASA workshop at Johnson Space Center, where right after this event occurred, which presented the spectrum, and we're going to use that particular set of data. The rest of the data from the other events are data that were gotten from the GOES satellites that NOAA operates, and NOAA provides them both on a CD-ROM and also on their website. GOES stands for Geostationary Operational Environmental Satellite, and it's basically a satellite in geosynchronous orbit that has particle detectors on it. They also do weather detection and all kinds of other things with these particular satellites. So what we do is we sum the data, which is from NOAA, comes in 5 minute averages over 5 minutes. What we do is we sum these to produce the cumulative fluence as the event progresses, and then we parameterize it using what's called a rigidity parameterization. The rigidity is basically the momentum per unit charge of the particles. Okay? And so we'll parameterize it using an exponential in rigidity, because it fits the data very well in terms of what... and then we differentiate this in energy and use that, the differential spectrum, as input into the transport calculation. So basically the J0 and R0 are fitting parameters to fit the particular spectrum. Now, what do the raw data look like? Well, these aren't really raw data. These are what NOAA puts out that come from the raw data. But for our purposes, they're raw data. This happens to be the Bastille Day event, which occurred on July 14th, year 2000. These are data from the GOES 8 satellite. These are the proton flux. These are 5-minute data. The red curve, which is at the top, is the total flux of protons whose energies are above 1 MeV. Excuse me, 10 MeV. The original data comes out on 6 channels, and they collapse it down into 3 for the figures. This is 10 MeV, the next one is 50 MeV, and then the bottom curve is 100 MeV. So basically, it's the total number of protons with energies at or above that energy as a function of time during the event. Now, the fall off for the 100 MeV curve is typical for a solar particle event. This little bump in here, which seems to have flattened the curve out quite a bit here, and actually shows up as a rise in the 10 MeV data, is because this particular event, the protons started arriving back here, but that coronal mass ejection that we just showed you takes about 17 hours to get here, so it doesn't arrive until the next day. So what we'll do is we'll take those data and we'll sum them up for the entire event. These are curves for various events. The most interesting curve, believe it or not, is this one right here, the purple one. That's the August 1972 event. Besides the fact that it gives the highest dose for any of the events that we're looking at, August of 72 was interesting because it was sandwiched in the middle, in between two Apollo missions. Right after one of the crews got, I forget which two missions it was, but right after the crews got back from one of the Apollo missions, this event occurred. And it was over with before the next one was launched a month or two later. The event with the hardest spectrum is hard to see because it's in yellow here, is February 56, and the spectrum for this is inferred since that's before the era of satellites. It was inferred by ground level neutron monitor measurements. Here the protons interact with the atmosphere, produce secondary neutrons that will reach the ground. And in this case, the monitors on the ground, their levels actually increased by 3,500% when this event occurred. To put it in perspective, that's about at least 10 times larger than any other event we've seen in the space era in terms of ground level. There were neutrons that were detected at ground level in this event whose energies exceeded a GeV. Okay, so this is an inferred spectrum, but it's extremely what we call a hard spectrum. It doesn't fall off very rapidly with energy. Very penetrating. Fortunately, the spectrum fit doesn't seem to have as many particles in it, so the dose is not as bad from this as you would expect that it might be. The big one that we look at is the August of 72. This is a plot of the cumulative spectrum as a function of time into the event. So this is 0700 on the 4th of August. This is 1000, 1200. These are all universal time, which is Greenwich time. 1400. Notice that between noon, actually between about 10 a.m. and 4 in the afternoon, over a 6-hour period, that the affluence level increased by over an order of magnitude. And then by the time we get into the evening on the 4th, it's starting to slow down, and there's not much change between the 4th and the 5th. So basically, for this particular event, within 24 hours or so, it was over with. Some of them last for as long as 10 days. Now, what we do with these input spectra is we transport them. In this particular case, we use a code that was developed at NASA Langley when I was there called BRINTRAN, which stands for Baryon Transport. It's basically a 1D deterministic code. Particles are energetic enough that 1D is a reasonable approximation. Transports all of the protons and their secondaries. The nuclear models in the code will calculate the proton, neutron, deuteron, alpha, helium-3, and triton secondaries from these interactions, and then transport those as well. We then, once we've transported them through the shield or the spacecraft structure, we then use the computerized anatomical man model. It's basically a computer model of a 50th percentile Air Force pilot. The body geometry is modeled in detail, and we use that as a human geometry model in order to calculate the body self-shielding effects for the various organs. So we transport all these through, and we pick different thicknesses of shielding. For these particular analyses, since we don't have a spacecraft, we just assume some nominal shielding amount. If you want to look and see what kinds of doses you'd get with a typical spacesuit, we put about 1 gram per square centimeter of aluminum in. It's actually a little bit thinner than that, but 1 gram is a nice round number. Very thinly shielded spacecraft, 2 grams per square centimeter. Most spacecraft that humans would be in would be at least 5 grams per square centimeter, so that's sort of a nominal number. And then we look at what we call storm shelters, which are areas that these people could go to for radiation protection purposes during one of these events, and typically we find that they need at least 10, maybe up to 20 grams per square centimeter or more. Now, if you're thinking about this area in terms of aluminum, density of aluminum is 2.7 grams per cubic centimeter. So 27 grams per square centimeter of aluminum is a piece of aluminum that's 10 centimeters thick, which is about 4.5 inches. Okay, so this is probably about 3 inches of aluminum. Aluminum, by the way, is not the best material. Now, for the man model, in order to get sufficient detail, what we actually do is we pick out the various points in the body, and then we find the equivalent thickness for 512 rays that cover all 4 pi solid angle from that point, and then we do the transport down those 512 rays. Now, fortunately, we don't have to do 512 transport calculations because after careful analysis, we've determined that you can, in fact, replace most of the body with water and get about the same results. And now all you have to do is know the water thickness. So if you do a transport calculation through a thick enough quantity of water and save up all the intermediate results, you can just interpolate to get what you need for each ray, and the calculation proceeds then much more quickly. Okay, this is skin dose for the July 2000 event. This is the one I showed you the spectra from earlier. This is skin dose in centigrade. Notice the top of the curve here is 1,000 centigrade, which is 10 gray. That's basically 1,000 rads. Okay, to put it in perspective, the time here is in hours. This point right here, where you're just about at the peak, is about 40 hours into the event. And this is what the curve looked like. The squares are the actual calculations for this particular spectrum of the skin dose using the CAM model. And the solid line is a fit that was done in an effort to try to extract a reasonable approximation for the dose rate. This is the skin dose from the August 72 event. This is 1 gram per square centimeter of aluminum, just like the last one. So this would be a nominal spacesuit. So you ask yourself, if the astronaut was inside the spacesuit, what kind of dose would they get if they got stuck outside? And the answer is a nasty one. Because if you look at this, this is about 1,500 centigrade, which means it's about 15 gray for a skin dose. Okay? And you're getting this in something less than 20 hours. The fact that there's a little bump in here, we ignored that when we did the fit, but the little bump in here is because for this particular event, at about 22 hours into the event, there was a CME that arrived, a small CME that arrived that increased the dose. It was almost like a second phase to the event. These are the dose rates. We got these by differentiating the dose curves as a function of time. So this is skin dose rate for the August 72 event. The top curve here is for 1 gram per square centimeter, which would be the spacesuit. The next curve down is for 2 grams, which would be a thin spacecraft, and then this would be for the nominal spacecraft. And notice the rates. For example, for the skin, the peak dose rate is about 1.4 gray per hour at about 10 hours into the event. Okay? Behind 2 grams, notice that it's reduced by about a factor of 2, because what you've really done here with the additional shielding is knocked out most of the low-energy protons. So what you're getting is high-energy protons, but the fluence of those is much less, because remember, those curves fall off as the energy increases. And then if we go to 5, it increases or decreases even more, down to about 20 or 25 centigrade per hour for the peak value. Those dose rates are somewhat important from the standpoint of biological effects, as we'll talk about in a minute, because the dose and the dose rate determines to some extent the effect. Okay? It's not just determined strictly by the dose, but also by how fast the dose is given. This is the bone marrow dose for this event behind 1 gram per square centimeter of aluminum. So this is somewhat akin to a whole body exposure. And it's almost 80 centigrade in a spacesuit.
Larry, where is the person located?
The person here is located basically in the center of a spherical shell whose thickness is 1 gram per square centimeter of aluminum.
Where, though? On Earth?
No, this is in deep space.
Okay, deep space.
Deep space. Okay, so it's about 80 centigrade, okay, which is about 8/10 of a gray, which is about 80 rads for the dose. We look at the bone marrow dose rate, it's up about 8.5 centigrade per hour. Again, this occurs a little bit earlier than it did for the skin, and this has to do with the fact that different components in the spectrum, this is basically the high energy part of the spectrum, because it's got to go through the shield, then it's got to go through the overlying body tissue. For the bone marrow, nominal thickness of body tissue that overlays the various bone marrow sites is about 9 or 10 centimeters, equivalent about 9 or 10 centimeters of water. So in essence, the bone marrow is shielded not only by the shield, but also by about 9 or 10 centimeters of water. So the doses and dose rates as a result are much lower for the bone marrow. Notice there's not much difference with that external shielding because in this case most of the shielding is being provided by the body. So the fact that I go from 1 gram to 5 grams of aluminum doesn't change the dose or the dose rate by very much in this particular case. Notice that we're getting some significant doses though, or we're getting dose rates that are significant for periods of time that are approaching a day. This particular one shows the distribution of the bone marrow dose. The acronym that we sometimes use is blood-forming organs, but it's really bone marrow. For various events, the different curves are different solar particle events. I apologize, this one's hard to see because it's yellow, but I didn't have time to change it before the presentation. But this curve here, the peak value of which is right here, is dose 0.5 for the bone marrow from the August 72 event, and the dose in that case in a spacesuit to that particular bone marrow point is about 350 centigrade. Okay, the minimum value is over here at 0.22. It's down around 30 or thereabouts, and I'll show you in a minute where those points are. But notice there's wide variation by almost an order of magnitude, for example, here between various bone marrow points. So when we say average bone marrow dose, yeah, it's an average, but recognize individual bone marrow sites are getting widely different values of exposure, which may or may not be important when you're looking at the biological effects. This is what happens if you go to 5 grams of shielding. Notice that it's reduced. It's gone from 350 to about 120 for point number 5. And down here it's down to about 20, so it's reduced slightly for the lowest point. The top curve, the yellow curve, is August of 72. The next curve down is October 1989. And then there's some other curves in here that this particular curve, the purple one, is November 60. Interesting thing, though. If you'll notice, there's August 89, September 89, and October 89. Usually about once every 11 and a half or 11-year solar cycle, we'll have one of these big events. In fall of 1989, we actually had 4 of them, but the 4th one was a little bit smaller, all in the span of 3 months. Okay, all different events. One of them was in August, one was in September, and then another one was in October. The one in October was quite large, which sort of set people back a little bit because we used to think, well, we have a big event, then it's over with, we don't have to worry about this anymore. Fact is, you have to worry about it all the time. Dose point locations. I'm not going to leave this up for long. These are the 33 points. The way they're listed is the first part of the entry is the actual cross-section plane in the body. In the case of 0.5, for example, which had the highest, it was the forearm. And then which bone it is in that plane. In this case, it was the radius. The minimum was the place that's most heavily shielded for most people. That's the cross-section plane that was the buttocks, and the bone was the hip. Okay, so it's not hard to understand why it had the smallest. Now, 10 grams per square centimeter of aluminum is a nominal storm shelter. What this shows is various values for the minimum value and the maximum value of the bone marrow dose for all of these different events. August of 72 is this one here. Okay, behind 10 grams of aluminum, which would be this storm shelter, the minimum value for the bone marrow dose, okay, in the buttocks region or in the hip region was a little over 12 centigrade. It was almost 52 centigrade in the forearm. The average, which in this case is a straight numerical average, was 28. It turns out that the average value that's usually quoted in the literature is not a straight numerical average. There's a different averaging procedure that's used here that takes some weighting into account, looking at thicknesses of material for the various sites. But it's kind of interesting that if you look, February 56, November 60, and August of 1972 are the largest. And then there's this October 89 event, 18.43, which was quite large for this particular grouping. Most of the rest of them are smaller, indicating that even though these things can be hazardous, they can be shielded from. What kind of limits apply? Well, right now, technically, there are no limits for deep space. All of the limits that have been promulgated for radiation fields in low Earth orbit, primarily protons. There are no radiation limits for deep space. But we can use the organ dose limits from NCRP report 132, which pertains to low Earth orbit, because it's basically dealing with primarily protons. The organ dose limits in what are called gray equivalent, and I'll explain that in a minute. That's probably a new one for some of you. Career limits are listed here. For the bone marrow, it's a different category, or it's a different grouping. There's not one number. I'll show you that in a minute. For the eye, it's 4 gray equivalent. For the skin, it's 6. If you're talking about an exposure in 1 year, the limit is 0.5 gray equivalent for the bone marrow, 2 for the eye, 3 for the skin, and then there's a 30-day limit. The career limit is designed primarily to make sure that all of these are designed to keep deterministic effects down, in essence. Deterministic effects meaning effects that depend on the dose, like cataract formation or skin effects, some sort of skin effects, blood changes, all that kind of thing, okay? As opposed to career limits, which are mainly oriented towards cancer induction. Okay, now, in order to convert dose to gray equivalent, you have to multiply by some RBE. And so basically, these are the recommended values from the NCRP in Report 132 for the RBE values to multiply your dose by if the particles come from these particular sources. So in our case, since it's protons, the RBE value is 1.5. This is some committee, which I happen to have been a member, his best guess as to what these are. In a lot of cases, these aren't measured, or they're measured only over a very limited range. In essence, what it's saying is protons that deposit 1 gray of energy, 1 gray of dose, are not going to create the same effect in terms of damage in the body as, say, 1 gray of X-rays or 1 gray of electrons or something else, okay? And so the RBE here is basically the ratio of the dose, in this case of protons, to the dose of the reference radiation, which would be X-rays or cobalt-60 gammas, to produce some desired effect, okay? That RBE is that ratio. And what it really means is that we take the physical dose, multiply it by this RBE to get a gray equivalent that we can then compare to the tables, for example, of biological effects from photons or gamma rays. So if you want to find out what dose is necessary to cause the astronaut to throw up, or to have blood changes, or for the skin to peel and fall off, okay, you could calculate. What you do is you take that number and you calculate the gray equivalent from it and compare that to the table, which means that the dose is actually smaller for these particles than it would be for photons or for gammas or X-rays to produce the same acute effect. These are not quality factors. Quality factors pertain only to stochastic effects, which are related to career limits, which are related to cancer induction and cancer mortality. Okay, these limits are assuming an astronaut career that's 10 years. These are effective dose, and everybody that's taken my 551 course knows what effective dose is, right? Effective dose is you take the physical dose for the organ, multiply it by the radiation weighting factor. That gives you an equivalent dose for that organ. Then you multiply it by the tissue weighting factor. Then you sum them all up. Okay? Now, for normal radiations, that's an easy way to do the calculation. For space radiation, it's a gagger, because the space radiation field has everything in it, which means you got to know what the contribution is from every component. Nevertheless, these are what the limits are given in terms of. So this is age at first exposure. So you're talking about a 25-year-old astronaut, for example, who would have some 10-year career. The career limits, these are in terms of sieverts. Okay? 0.4 sieverts for the female, 0.7 for the male, ranging up to people that are more my age, which if I went up would be one, in the case 3.0 here. So I could get lots. And the reason is because the probability of cancer induction at my age from some exposure at age 55 is much less than it would be for somebody at age 25. Typical cancer induction being on the order of 20 years. Okay, now notice this particular number here, because if you do some conversions, this number is actually smaller than the annual limit for an organ exposure, if you converted that organ exposure to an effective dose for the female, okay? And this has got to do with cancer induction, and in the case of the female, the primarily sensitive tissue here is the breast. So anyway, the limits are different for males and females, and it's got to do with biology. Okay, so let's take a look. Well, what are the effective doses? These calculations Jenny did, these are for the August 1972 event. These are the shield thicknesses here, same ones we looked at before. This is the effective dose calculated using the tissue weighting factors. This is the average bone marrow dose equivalent. Okay, so this is, if you will, the equivalent dose for the bone marrow organ, which people have typically used as a surrogate for effective dose in space radiation calculations. Okay, now the question is, how good is that? Well, here's the percent difference. Notice that they're quite large. The answer is, for years we've been using this as a surrogate for effective dose, and it's lousy. At least for solar particle events, it's lousy. Notice also that the average bone marrow dose equivalent is smaller than the effective dose, which means that in effect, had we had somebody out there and we were using this for a limit, in fact, this was actually what they got for an effective dose, which means their cancer probability and the cancer induction and mortality probability was much higher than what we'd originally would have calculated. Fortunately, we didn't have anybody out for any of these. Now, in the case of galactic cosmic rays, just for comparison, the differences are minimal. They're on the order of 10% or thereabouts. And the reason is because the galactic cosmic rays are energetic enough, okay, that all of the organs get essentially the same kinds of doses, no matter where they are. If you look at the distribution of bone marrow, it's much narrower for the galactic cosmic rays. And so the result, for example, is that there isn't a lot of difference between the average bone marrow dose and the effective dose, whereas that's not the case for these. Okay, so this is the effective dose for the July 2000 event, which I put up just because I showed you the spectrum. It's not quite as bad as in terms of differences as the August 1972 event. And notice that the effective dose values are much smaller than they were for the August 72 event. The percentage differences, though, are still about the same. What's happened here is the spectral shape is not very different. The only thing that's different is the magnitude. Okay, so what kind of acute effects could we see? Well, if we're in a spacesuit, for example, and we look at the bone marrow doses, something on the order of a gray delivered in a day could produce some blood responses, could see some changes in blood count. It's also possible meaning that there's a non-negligible probability, probably on the order of 20 or 30%, that you may have some gastrointestinal problems and may induce vomiting. Now, if you're in a spacesuit, vomiting is not good. Okay? Because basically there's no place for it to go except in the helmet with you. And the concern here is that if you get an astronaut in a spacesuit that starts vomiting, they're probably going to die. And the reason is because they're not going to be able to breathe. Okay? So even though this by itself wouldn't be fatal, in a spacesuit it's liable to be fatal just because of the fact that you've got that complication. Skin doses, 15 to 20 gray, could have some erythema, which is a fancy word for reddening, sunburn. The interesting thing about these particles is not only do you get burned on one side from the particles that come through, for example, if you pick a point out on your chest, not only do you get exposed from this side, the particles also come through from the other side and expose your skin. They're energetic enough to pass through your body and deposit energy from both sides. So you get a sunburn from both sides on the front, both sides on the back. So turning over doesn't help. Okay? Now, moist desquamation is basically a fancy term for what? You get blistering and the skin starts to come off, right? It starts to come apart. That's not good either. That wouldn't even be good in a spacecraft. You just don't want to have major medical problems on your way to Mars. Doses inside the nominal spacecraft, however, would reduce these down to where probably the most severe effect we'd see from most of these is some skin reddening. Okay, so you can reduce the acute effects if you can get that astronaut back into some sort of protective cover. August of 72, for example, eye doses. In a spacesuit, you're going to have problems with some skin reddening of the lid. You're going to see some problems with your cornea. You're going to have cataracts. Inside the spacecraft, these two would be reduced and only cataracts would probably result. But cataracts are not good, particularly in space. It makes it hard to see the instruments. Yes?
How quick did they form?
I don't know the answer to that. I do know that they have some problems now with some astronauts that have had some cataracts. And they haven't received exposures anywhere near this. A couple of years. I don't think it would matter so much for a short mission, but for a real long duration mission, it could create a problem. Okay, background change. That's because I can't get the black here to change color. Actually, it's to wake you up. I promised you a look at solar particle event dose forecasting. And one of the things that we've done, must have missed one. Yeah. Let me start out by saying here that at present you can't forecast doses or fluences before they occur. I can't tell you tomorrow that today that there's going to be an event next week and this is how big it's going to be and this is what you're going to get from it. People would like to be able to do that because if you knew it was coming, you wouldn't send somebody out. But at present time, it's not possible. So what we're doing is sort of the next best thing. We're working on methods to forecast doses and to forecast the dose buildup over time based on the first few dose measurements that come in when the event starts. Okay? This particular project just got some support from NASA's Living with a Star program out of Goddard Space Flight Center. So we're kind of excited about it. Two approaches we use: artificial intelligence. In this case, we're using a sliding time delay neural network that's been worked on by Jenny Nazila Tehrani, who was my first PhD student here. Garth Ford and Dr. Hines and myself have worked on this. I'll show you some results here in a minute, but not very many because Jenny's still producing them for a thesis or dissertation. We'll probably have her give a presentation of that when she finishes. I just put her on. And then there's also a second approach that was taken using Bayesian inference methods by a former PhD student of mine, John Neal, who now works out at the lab. And so we're continuing to work on this. Let me show you some results. These are some predictions that John made using the Bayesian methodology. This is for a dose forecast. This is for the November 2001 solar particle event. And this is the dose forecast using dose measurements up to 2 hours into the event. Now, let's put it in perspective. The actual dose profile is the solid curve. The predicted profile is the dashed curve, which here is right below it. They're about 5% or less apart. I know it's a little bit hard to see in the back of the room, but the arrow is almost right on. Now, where are we in this particular event? We are down, see if I can get it over a little bit more. No, too far. Right about in there. At this particular point in time, the total exposure 24 hours into the event is approximately 250 centigrade. At this particular point in time, we've gotten about 0.7% of the dose. So the event started, the crew member's been exposed to 0.7% of the dose, and we're predicting the dashed curve for what the dose is going to look like for that crew member as a function of time. What the actual curve will be at the end of the problem is it'll be the solid curve. So the prediction's pretty good 2 hours into the event for this particular one. I wish they were all this good. Now, because of fluctuations in the dose that occur, because these things aren't really smooth curves, the data comes in and the particle distributions bounce around some. This is 3 hours into the event, so this is right here. This is a little over 1% of the dose. Here's the actual dose profile and the dashed curve up here, which is now different by about 20%. At the high end, we're over-predicting the final dose by 20%. Okay, 3 hours into the event, we now like this curve, but the real curve is still this one. So it's off by a little bit. Fortunately, we're over-predicting because that means we're conservative. Chances are whatever action we take as a result of this are going to be adequate to keep the astronauts safe. Okay, this is 6 hours into the event. So we've gone 2, 3, and 6. This is 6 hours into the event. So where we are is right here. The dose is about 20 centigrade at this point, so it's not quite 10% of the total dose for the event. And you can see that the curve settled back down to be pretty close to the actual profile. So it seems to work pretty well in terms of predicting the profile for this particular event. For other events, it may be off by 30 or 40%. And in some cases, we don't know why yet. Some of it has to do with quirks in the particular events and the way the actual dose curves bounce around as a result of the incoming fluxes. But it's got some promise. This is the only one I'm going to show from the artificial neural networks. STDNN, it stands for Sliding Time Delay Neural Network. Basically, it's a neural network that was primarily developed by Dr. Hines, but it takes variable time delay inputs into this network. It's a feed-forward network, and what we're doing now is feeding it doses early in the event. We're asking the neural network to tell us what the total dose is going to be. So in other words, this is asking the obvious question. How big is this event going to be? What kind of dose am I going to get at the end of this thing? And the results are here. This is the dose in centigrade. This is for the August 72 spectrum. Okay, the actual final dose in this particular calculation, okay, I don't remember the combination of shielding and so forth that this is for, but that's somewhat irrelevant. All we care about is how well the dose is predicted versus actual doses. The actual dose that we're expecting to see here is about 960 or 965 centigrade. Okay? This is what the actual dose buildup curve looks like as a function of time. So you can see that it really doesn't get to that point until about 4.5 days into the event. Okay? What the top curve shows here, this blue curve that bounces around, is this is the prediction for this value at that particular point in the event. So if we're back down here within the first couple of hours of the event, which is barely off the axis here, we're already predicting very early in the event about 925 centigrade for this particular event, even though we haven't seen it yet, all of the particles from it. And it turns out to be a reasonable prediction. Now it bounces around a little bit. Here we get up almost to 1,000 by a half a day. But you can see that within the first day and a half or so, it's settled out right on the value. Now, where are we in terms of the dose at that particular point in time? Well, we're still down in here at about 20%. So we're within 5%, almost right off the bat, never strayed by more than that for this particular prediction, and what the total dose is going to be. So it seems to work relatively well. And Jenny has some same types of predictions for dose as a function of time, and she'll show them to you later. You can come to her dissertation defense. Okay, so that's forecasting doses. Seems to have some possibilities. Concluding remarks. Organ doses received from the large events are hazardous to crews in deep space, or they can be. Exposures that are survivable with proper medical treatment on Earth may not be survivable in space. That's a key point to keep in mind. Aside from acute effects, a single large solar particle event can expose a crew member to an effective dose that exceeds their career limit. Typically in the past, we've always thought about, well, career doses apply to galactic cosmic rays. Solar particle events give you acute doses. Well, they do give you acute doses, but they also contribute to career dose. Career effective dose, okay? And so you have to really be careful about this. Just providing enough shielding to cause the astronaut to survive the initial solar particle event may not be adequate if the result is that they have a 50% probability of dying of a fatal cancer. So, that needs to be considered when you're looking at shielding. Now, due to the relatively soft energy spectra, solar particle event doses, as we've seen, can be substantially reduced with adequate shielding. In reality, probably at least 20 grams per square centimeter of aluminum or equivalent is adequate in most cases. I didn't show the result there, but for that August of 72 event, if you had 20 grams per square centimeter of aluminum, the bone marrow dose is less than a centigrade. Wow. So it's possible to reduce it down. Now, research needs. Well, what's really needed here are data on biological effects for solar particle event protons at doses and dose rates that are observed in these events. Let me give you the illustration of what I'm talking about. Doses are comparable to those for clinical exposures. Spacesuit numbers were comparable to what you'd see for a clinical exposure. A couple of hundred centigrade, a couple of hundred rads, okay? The difference is in a clinical exposure, you get those in a couple of seconds or maybe a couple of minutes at the most. In this case, you're getting them over a period of a day or so. The difference in dose rate is significant in terms of the effect that it has on the body. So even though you have the same dose, you don't have the same biological effects because the dose rate that it was delivered at was 2 orders of magnitude or more smaller. The problem is that we don't know what the biological effects are for protons at these energies and dose rates. We've got proton machines that provide energies a couple of hundred MeV, Loma Linda machines used for radiotherapy. It provides doses at these dose levels, but it doesn't provide them at these dose rates. And so what's really needed are dose rates, okay, data for the dose rates that you see in these kinds of things in order to determine what the biological effects are. Solar particle event dose rates, however, are above the low dose rate limits that are promulgated by the various advisory bodies, NCRP, ICRP, UNSCEAR. The largest low dose rate limit, where you can consider it to be a low dose rate and apply some various low dose rate factors, is 0.1 gray per hour. And as we've seen, the doses in these events can far exceed this. So the problem is it's sort of never land here. So from a biology side, you really would like to know what the effects of these are on the body. I'll be happy to answer any questions.
Do we have any questions or comments for Dr. Townsend? Ron?
First of all, that Soho, where is it? Did it go around the sun? And how far away is it?
Yes, and I don't remember. It's at it's in a sun synchronous type orbit or some sort.
And it's closer than we are?
Yes.
And the other question I had was whether there was any, you acted like, you said that the events seem to be sort of surface event, like some magnetic field. Nothing deep going in it.
There are some occasionally, but it's hard to tell exactly what's going on. It's only been recently that they've really had some good information as to what's going on through some of these satellites, for example, like SOHO, and the Japanese had a satellite, Yoko, and some others that make these kinds of measurements.
Was there any kind of a light signature? Did it give any kind of a...
Yes and no. For a long time, it was thought that solar particle events came from solar flares. And there's a lot of solar flares that give off X-rays and optical signatures. The August of '72 event, for example, there was an optical. You could actually see the flare optically about 45 minutes before the particles started arriving. Okay, but the problem is that not every solar flare produces energetic particles. And then they found these coronal mass ejections when they started looking out in the corona, found out that most of the large events were associated with coronal mass ejections. The problem is that there's about 2.5 coronal mass ejections a day, and probably 1 or 2% of them produce any measurable particles that you're interested in. The other thing you'll notice in some of the images, we're looking at it from the side, right? So they're going off in some different direction. So even though we would say, well, we've only observed one large event every solar cycle, we're only subtending a very small solid angle. It's quite possible that there's 10 or 15 of these or more. They just happen to go off in directions that we don't see because they're behind the sun or something else. And we don't have any particles to detect them. So there's been a lot of work on instrumentation to detect the composition of these things as they fly off into space in order to try to determine how much mass is in there, what kind of energies the particles have, and so forth. And from a forecasting standpoint, that information would be nice, because if you could get that before the particles start arriving, then you could take these things that we do and make predictions, because you can convert hypothetical fluxes to doses. You could actually start making predictions before the event ever arrived, which would give you some more lead time in terms of taking mitigative action. Pardon me?
You can get people inside.
That's right. You can't get them inside quickly. Astronauts, it's not like coming in out of the rain. You don't open the screen door and walk in. First off, there are no screen doors. And secondly, it takes a while to get in. So,
I may have asked you that before. Do they do chromosome aberrations? I don't know what you said.
I think they're doing them now.
They're doing them now? Did they start this recently? Do you know? I don't know what you said.
I know there are some data. I don't know whether they do chromosome aberration screening on every crew member or not. It's hard to get medical information. Astronauts don't like to receive medical information, or they don't like to have medical information given out to the media, to the press, or even to people outside the organization. So it's hard to get medical information.
Andrew?
You commented early on, you said that there were GeV type particles coming out of the sun and other places during these events. Of course, in the reactions that we're familiar with, for example, fission, you just talked about 180, 200 MeV, and then thermal things, even something as hot as the sun, you're talking about a few keV. How would you have a reaction that would be, what kind of reaction would you have?
Oh, you're not producing the GeV particles inside the sun. What you're producing them with is the magnetic fields that are in space between here and the sun. Because you've got a plasma that comes off the solar wind, right? It's got a magnet. There's an interplanetary magnetic field. When these plasma ejections, coronal mass ejections, and the like occur, okay, the shapes of them are dictated by the underlying magnetic field. Maybe there's some loop that got cut off, and that's why it's leaving the surface of the sun, carrying material with it. Well, those magnetic fields interact, and what you get is you can get a cyclotron effect where the particles, for example, will oscillate back and forth across the wavefront and gain energy just like in a cyclotron, okay? And by the time the particle gets to you, it's got lots of energy. Well, now that energetic heavy particle hit some nitrogen nucleus somewhere in the atmosphere and ejected an electron. Maybe it hit one of the electrons head on. So that's where the particles come from.
Any other questions or comments for Dr. Townsend? Okay, as usual, we do have refreshments down on the second floor, and everyone is invited. But before we adjourn, let's express our appreciation to Dr. Townsend.
Yes. It's hard looking at the range sometimes.
I am